Yeah, hi everyone, welcome. I'm Jim, I'm the CTO and one of the co-founders of Irreducible. I'm going to tell you about Binius and the programming model that we use to express verifiable computations. So this is going to be a technical talk. Hopefully you don't need to know that much about zero knowledge and hopefully you learn something. But first, I am obligated to tell you about Irreducible and who we are. So Irreducible is a startup that as of 2025 has a Berlin-based headquarters. We're accelerating the zero knowledge revolution with the world's fastest proof generation. This basically means our whole mission is we go every day and try to build the fastest technology for verifiable computing. Why? Because first, for blockchain applications, I believe this is the only way to securely scale blockchains and peer-to-peer systems. We need cryptographic verifiable computing in order to get, the worldwide adoption without compromising the essential auditability and transparency guarantees that make blockchains important. But there's also future applications beyond the blockchain space that I'm excited about. This is a fundamental technology that can be used to verify content authenticity, and in a world with more generative AI, hopefully combat deepfakes, potentially be used to check the safety and bias of machine learning models or AI models running remotely. And then there's all the zero knowledge and privacy applications. So there's a lot to be said about this. You can come find me afterwards if you want to hear what other applications I'm excited about. What Irreducible is doing is we're building a vertically integrated stack for verifiable computing. So this is actually a lot of technology going from the top layer of virtual machines that can run some computation that you want to prove and verify succinctly, through the proof system layer, which for us is Binius, and we have a lot of technology in the custom compute layer that this little box doesn't do justice to. Basically, we're designing custom hardware, we're running servers, we're designing hardware instruction set architectures, building a system on chip, custom drivers, custom languages for all this stuff. It's very cool. But I'm going to focus on the middle for today. And on the virtual machine side, we're partnering with some other companies in the ZK space like Polygon and RISC-0 to develop virtual machines. And the talk is going to be about how do you express a computation that is provable or succinctly verifiable. And at the very top, we want to be able to verify programs that are just in Rust, like regular programs that you would run. And how are you going to do that? Well, you're going to compile this Rust program to a virtual machine architecture. So for example, RISC-V, and then you need to prove the execution of your RISC-V machine with a proof system. So Binius is the proof system that we're developing. It's based on binary fields. I'm not going to talk too much about that, but it's sort of a modern alternative to other proof systems that you might have heard of, like Halo 2 or Plonk 3 or Stew. And a proof system has a prover and a verifier. They're communicating. The prover is doing a lot of work, and the verifier is reading a proof and not doing that much work. And they both need a front-end API, which is how you're going to express the computation. You've probably heard about ZK circuits, like you're programming a ZK circuit and then you're going to prove a circuit. We're not talking about circuits. We have another framework for expressing computation. So, what can we prove with Binius? I'm going to give a totally random example here. So let's say you're escaping a maze. Imagine you're in the middle of a maze in some cornfields and you don't know how to get out, and you actually don't even know if you can get out. You don't know if there's an escape to this maze. So how would you figure out if you can get out of the maze? Well, one is you can wander around in circles until you get out or not. That's not very good. The second is I can shout directions at you, and then you're going to follow my directions, and I'm trying to convince you you can get out, and you're going to follow my directions, and eventually you'll end up at the exit, and you'll walk out, and you'll be convinced that there was an escape to the maze. And then I'm going to say basically that there's some way to succinctly convince you, without you walking through the whole maze, that there's some way for you to get from where you are to the exit and walk out using M3, which is the programming model for Binius. So let's say, your start location is 0, 0, and the exit location is 100, 0, and you're just going to follow my commands. So I shout step up, and you're going to have your location state, which is like a two-dimensional coordinate in this grid, and when I shout step up, you're going to update from x to y plus 1. Step down, you'll update your y coordinate. Step left, you update your x coordinate. These should probably be x's. Yeah. There's one problem, which is if you just do this all the time, you might run into a wall. So you actually need predicates for each of these commands. Like, you can only follow the command if some predicate is satisfied, so you can update from x plus y to x plus y plus 1 if that cell is empty, if there's not a wall there. So we're going to express this in this sort of weird graphical model that looks like a state machine, but instead of it just being a state, we are going to think about these green boxes as tokens that you can take and you can put back. So you have a place where you can put your location tokens. And if you want to step right, you pick a location token from this spot, and you go and modify it, and you can put it back. And what I'm claiming is that if you initialize this diagram with one thing in the location spot, which is 0, 0, and you follow these transition rules, and you end up finally at 100, 0, then it must be the case that there's an escape to the maze, assuming that the transition functions have the predicate of the walls being empty. So the new thing here is that you're following these commands, but there's this token-based model where it's like I can pick up the location token and I can put it back after some updates. I haven't talked about walls yet. So how do I check that there are no walls? I'm going to introduce a new place and a new type of token. So the location tokens were the green tokens, the map tiles are the blue tokens, and a tile has a XY coordinate, and either it's empty or it's a wall. And so this is the step up transition. So when I step up, I have to take my XY coordinate from locations, and I also need to take an XY plus 1 empty token from the map tiles. And if I can take these two tokens, then it means like I am at XY and the place I want to go is empty, and then I'm going to put back my empty token, so it returns there if I ever want to try to go through there again, but I'm going to update my location. So this is now, I have this mechanism for checking for walls, and basically if I ever shouted to go through a wall to you, you just wouldn't be able to pick up the empty tile. It wouldn't be there, it would be a wall instead. And now I'm adding doors. So
didn't see that coming.
Okay, how are we going to handle doors? What can I do with a door? When I shout open door, you're going to stay in the same place, but you're going to try to open the door. You're going to update the map, so where there was a door, now it's an empty spot. And in order to open a door, you need to take a location token. You need to take a token with XY plus 1 and a door in the place where you want to open the door. And you have to have a key. And the way I've written this is actually the key gets stuck in the door and it goes away forever. So you might like start with a finite number of keys, and then every time you open a door, it goes missing. So if you don't have any keys, you wouldn't be able to open the door, you wouldn't be able to follow my command. But then, so what happens, well, I'm going to put my location back to the same one. I'm actually not going to move. I would have to move on like, say, the next transition. But I'm going to take where there was an xy+1 door and put back an empty spot in its place. So this is the sort of transition rule for opening a door. This is basically the model. This is the whole model. And what I'm not really going into in this talk as much as why this is efficiently provable. But to say it briefly for the people who are more familiar with zero-knowledge techniques, we can check these. What we need to check, I thought there was a slide, actually. Oh, well. Wait, oh. I feel like I have time to do this. I think there's a skipped slide, if I can.
Oh yeah, you just need to remove it.
Wait. Shoot. Oh, well, I guess it's here. Okay.
It's a slide.
This is briefly a bit about like why this is an interesting model for proving. And this is an efficiently provable paradigm. If you can express the rules of provability as being consuming tokens, putting tokens back that are derived from them, having predicates on when these fire, we can use cryptographic arguments. And so if you go and look through the Binius documentation, we have slightly different language for this stuff, but we can basically use permutation arguments to check this channel balancing equation, that you're going to put some initial tokens in some places, you're going to expect some final tokens, and if the initial tokens plus the set of all the tokens that you put into a place equals the set of final tokens plus all the ones that you've taken away, if that's true, then the statement must be true. And this is really powerful, and it lets us express arbitrary computation. That's a big claim. What does it mean that this model is powerful enough for us to express arbitrary computation? Is there a slideshow? Well, virtual machines are mazes, right? So the location that you're in is the program counter. It's pointing at an instruction. The map tiles are main memory. Remember how we could read a door and then put back an empty? I can go and modify memory by having, cells with an address and a value. And the commands that I'm shouting at you are instructions. So we, in Binius, are going to express the semantics of our virtual machine using these commands. If I am in a location where my program counter is pointing at an add instruction and the memory satisfies the predicate of add, then I can accept that add instruction. And so Binius can prove mazes, Binius can prove VMs. I glossed over a lot of technicalities. I want to say that the model I presented here is a well-known model in programming language theory called colored Petri nets. They're very well studied and are amenable to formal verification. M3, which is the Binius arithmetization, is closely related. There are some technicalities. You need to add timestamps for security, but it's very, very closely related. And if you can model something as a colored Petri net, you can model it as a Binius M3 program and prove it. And that's my talk. So here's where you can learn more about Irreducible. If you want to learn more about Binius, our proof system, and M3, binius.xyz is the place to go. And does anyone have questions?
I'll just say we have Irreducible t-shirts at the entry door, but only for the people who ask questions.
Right.
But encourage to ask questions.
I have a question here, and maybe this is very example-based, but is the maze example zero knowledge? Because at least how you put it, it seems that I could read, let's say, or learn the path, basically.
No, there is nothing I talked about that gives you an idea of why this would be zero knowledge.
Yeah.
It could be. This programming model could be. This sort of gets into the how you take so again, the paradigm is you set up the maze, and then all I'm trying to claim is that if you start with some initial tokens, then you'll be able to reach the state where there are final tokens. The verifier shouldn't need to do every command. Instead, it's going to get compiled into the proof system, and there's going to be polynomial magic that happens that convinces you that the final state is reachable from the initial state, but you're not going to do every command. You're going to check polynomials, and you're going to verify this succinctly. That was not really part of this talk. Yeah. And then there would be, if you wanted to make it zero knowledge, you would add random blinding factors to your polynomials, and then it would be privacy preserving.
Fake doors.
So
Something like that.
Maybe another one. The M3, okay, this is kind of like a new way of arithmetization, basically.
Yes.
But you use kind of the IOPP or like the star. Do you use also like your own IOP for that?
We use a multilinear IOP.
Okay.
So it's using a toolbox of things that are familiar to people. We use sum checks. We use grand product arguments. We do permutation arguments. We use Fry for the PCS. That's actually, if you go to binius.xyz/blueprint, the blueprint kind of lists all the polynomial IOP ingredients that go into the Binius proof system. Yep. Chris?
So in your example, you used things like x+1, y+1, so arithmetic operations.
Yeah.
But I mean, because in binary fields this is more complicated, I assume arbitrary arithmetic operations are not one of the elementary operations.
They're not elementary, yeah. They would be constrained with nonlinear constraints. And so we have a sort of mapping of, so what does a Binius proof consists of? You have a witness, which is a list of all the events that will ever fire. So every time like arrows go into a rectangle, that's like a transition event, and we list out for every one of those boxes all the events. And so for something where it's like you're putting back x+1, you would have a table that has 3 columns like x, y, and z, and you would have a predicate constraint that z equals y+1 as integers. That would not be a, say, algebraic thing in binary fields, but it would be like a nonlinear constraint that we can check bitwise pretty efficiently, and then you would put the xy token in one place and the xz, where z is y+1 in another place. Does that make sense?
Yeah. So it's essentially just transition functions, and that's it. No real operations. If you want to use operations, you have to build them or take them from some library or something. Right?
Yeah. So in Binius, in the actual programming framework, we have these tables, and then we have a library of gadgets, and gadgets encapsulate the common nonlinear constraints that would be common. So we have like a U32 addition, we have like a barrel shifter, bit shifter, and then you can actually implement those predicates using lookup arguments or bitwise constraints or binary field operations, or you have a lot of tools available to do that. Yep.
What's the cost of interacting with the channels versus doing computation? Is that
So every element, we define a table and a flushing, we call them a flushing rule, but it's like every arrow from the table means that every event that fires is going to, send something, and that ends up being a leaf in a grand product argument. So it's proportionally linear. We can measure, basically, I don't know the numbers off the top of my head, but we measure the throughput of our grand product arguments. I can actually show you where to find these numbers online. If you go to bencher.dev and you search for the Binius project, there's a site that lists open source benchmarks, and we put stuff up there. So we would look at the grand product argument of doing a grand product over a table with 1 million entries, and then you would divide by 1 million, and then you would get the sort of latency cost or throughput cost of doing of flushing one event. Yeah. So, but I guess a channel flush corresponds to 1 leaf in a grand product argument per event. I think there was one more question.
Yeah, are there limitations compared to other proving systems?
So there are a couple of tools that we've gotten rid of. It is just as expressive. So this is, I mean, you can express any problem in NP in this language of M3 or colored Petri nets or whatever. There are some constraint systems in like an air that would maybe be more efficient to prove than in M3, but we think that in VM design and in basically all of the real constraint systems that we've seen in the wild, M3 is more efficient. Why is it more efficient? Because we can handle control flow through flushing, where most other proof systems have some combination of control flow coming through like selectors, where if you need to do an if or an else, then you like do both of them in parallel and then you multiply one by one and the other by 0. If you do control flow through flushing, you're actually only paying for what you execute. And so it ends up being really efficient for a lot of natural use cases, including VMs.